All right, good morning and welcome to Unit 6. So today we are going to delve a little bit more in depth into probability and look at some specific types of what we call probability distributions. So let's think about what that means. So when we talk about a probability distribution, we're looking at a set of different options and how likely they are to happen. So in our first example today, let's pretend we had a class of 30 and the instructions were to count up the number of children in your family, including yourself, right? So we are using what is called a random variable, and we are calling that random variable x, and we are letting x stand for the number of children, okay? So the way that I would read this probability distribution right here is across the top, I have my random variable, I have x, and that is the number of children that are possible. Okay, so it looks like in this particular class of people, the smallest number was 1 and the largest number was 8. Okay, and what I want to remind you of is in any probability distribution, in order to be valid, your probabilities have to add up to 1. And so the fancy way of writing that you may see sometimes is people will use this Greek symbol sigma, and that just means the sum. So the sum of the probabilities have to equal 1 in order to be valid. The other thing that has to be true is that your probabilities can't be negative. So they have to be between 0 and 1 inclusive. And when I say inclusive, that means it can be equal to 0 and it could be equal to exactly 1. Okay? So what's going on here? Well, this is what is called a discrete random variable. And so I want to remind you of what the word discrete means, and I want to say we went over that back in it was either our first or second unit. So a discrete variable is a variable that can't just be any number. It's not always whole numbers, but typically we think of it as being whole numbers. So for example, you couldn't have 0.5 of a child, right? So you could have one child, you could have two children. There are gaps between 1 and 2. You're jumping over some numbers in the middle, and that's what makes it discrete. A continuous variable would be something like weight, right? So if I weigh an item, it could be 120 pounds, it could be 120.2. We could get as accurate with that as we want, and we could literally have any decimal as our variable. It's continuous. There are no numbers that we have to skip when we're talking about weighing an item. Okay, so number 1 says, is 5.7167 a possible value for x? The answer is no, because you can't have part of a child. You could have 5 children or you could have 6, but not anything in the middle. Okay, so number 2 says, with that in mind, calculate the probability that x is greater than or equal to 3. Well, what does that mean? X represents the number of children, right? So what we're calculating here is what's the probability that your family has greater than or equal to 3 children, or in other words, at least 3 children. Well, that would be everybody from here over, right? So if I add all those probabilities together, 9 plus 5 plus 3 plus 2 plus 1, adds up to 20 out of the 30 people in this class. Okay? And the way we would interpret that is the probability that a randomly selected student has at least 3 children in their family is they wrote 20 out of 30. That will also reduce to 2/3. Okay? So that means 2/3 of the people in this class have at least 3 kids in their family. Something that we want to get in the habit of doing when we have a probability distribution is drawing some sort of graph, just so we can get an idea of what's happening in this class as a whole. And the most likely graph, or the most common graph that you're going to see, is a histogram. So the way they've drawn this histogram is each bar represents a different number of children, and then up the side, right here, that is the probability that it happened. So if you notice here, bar 1, so that represents 1 child, goes up to 3 out of 30, right? The most common event was having 3 children. That goes up to 9 out of 30 on the y-axis. So how does this help us? Well, a graph lets us see what is called shape, center, and spread. Okay? So when I look at this distribution and I'm thinking about where the center is somewhere around right here, but I want to tie an exact number to that because it may not be exactly 3. And generally, when we are looking at a graph, we want to find the mean or the average because that's going to tell us roughly what's happening in the middle of this graph. Okay? So when we find an average, or when you did it back in elementary and high school, what you may remember is that we would add together a set of numbers and then divide by how many there were. Okay? So you may be thinking, well, to find the average, I just need to add together the numbers 1 through 8 and then divide by 8. And when you do that, that gives you 4.5 children. Well, that falls over here. And I can tell from the graph that 4.5 is not the center. So why doesn't just adding together the number of children and dividing by 8, why doesn't that work? Well, it's because each of these numbers of children is not equally likely, right? There were more people in this classroom who had 3 children in their family than there were who had 1 child in their family. So when that happens, the way that we find your mean is this right here. We take each value times the odds that it happens, and then we add that together. So we're not just adding 1 plus 2 plus 3 plus 4 all the way through 8. We're doing 1 times 3 over 30 and then adding that to 2 times 7 over 30 and so on. Okay, all the way down the line. And what that does is it allows for us to do what's called a weighted average. And it's similar to what I do when I calculate your grades, right? Tests way more than quizzes. I don't average those evenly into your grade. Okay? So I give more weight to the numbers that happen more often. And so when you type this whole big long thing in your calculator, you get that the average or the mean is 3.3. Okay? So how would I interpret this? So what this means is the average number of children in a family in the long run in this class is 3.3. It does not mean that every single class of 30 that I could ever choose would have an average of exactly 3.3. It means for this specific class, in the long run, I get 3.3 children on average. Okay? So what about, that's the center. What about the shape of our graph? Okay, well, the shape of our graph, I can tell it's leaning towards the right, and that's because I have a right tail down here, right? So this graph is skewed to the right. And then the last thing is our spread. So usually when we talk about spread, we want to look at standard deviation. Now, I'll be honest with you, you can do the standard deviation by hand. You probably don't want to. I've got the formula written down on the back, but it will take you a long time to do by hand. So that's when we pull out our handy dandy calculator. And what you will want to do is click the stat button, okay, which is right here. And you're going to want to click enter when you get to edit. And so I already have this typed in, but what I did is in the first list, I just typed in the possible number of children, so 1 through 8. In the second column, I typed in the probability that each of these family sizes happens. So what I actually typed in line number 1 here is I did 3 divided by 30, and it changed it to a decimal for me. So I did not do that by hand. Okay? Once you have those in, you're going to click stat again. And this time you're going to click the right arrow and scroll over to calc. And we have one variable here. Okay? And so this is a little bit different than what you saw a couple units ago, but still similar. So your list should say L1 because our random variable X is in L1. What is different here is our frequency list. This time what you're going to do is you have a second column, and that second column tells us how often each number happens, and that's what frequency is. So what you're going to do is you're going to click the blue button, second, and then 2, and that will put in L2 as your frequency list. And then you're going to click calculate, and what you will see is it actually spits out for you that average that we just calculated by hand of 3.3, and it also spits out your standard deviation right here so that you don't have to do that by hand, okay? So our standard deviation is 1.59 roughly. So what does that mean? Okay, well, if our standard deviation is 1.59, what that tells us is the number of children in a family typically varies by about 1.59 children from the mean of 3.3. So what that means is most people fall within about 1.6 children of 3.3. So think about what that means. If I add 3.3 plus 1.6, that would be 4.9. Which falls, somewhere right in there. And if I did 3.3 minus 1.6, that would be 1.7, which is somewhere right in here. It's telling us most people fall in this section of the graph, which makes sense. That's where our taller bars are on the histogram. So that's how we interpret standard deviation. Okay? So I've got the formulas written down here for you in this quick notes box for the mean and the standard deviation. But again, especially with standard deviation, I would strongly encourage you to use your calculator. Okay, so let's look at one more example. So Home Alone is a series of American Christmas family comedy films created by John Hughes. There are 5 Home Alone movies. I actually didn't know that. I've only seen the first couple. Below is a probability distribution of the number of Home Alone movies watched by a very large sample of high school students. And this time our random variable x is going to stand for the number of Home Alone movies watched. Okay? So we've got our probability distribution here. And the first question we're asked is, what must be the probability that someone watched 3 of the movies? Well, if you remember, in order to be a valid probability model, these probabilities have to sum to 1 or to 100%, right? So if I add together the probabilities I do have, they add up to 0.92 or 92%. That means that 8% of people must have watched 3 of the 5 movies. Okay? Part B, what does it mean when it says find the probability that x is greater than or equal to 1? That's the probability that if you select a student, they have seen at least 1 movie, so 1 or more. So basically, if you think about that in the table, what that does is it's all these people. So it cuts out the people who haven't seen any of them. So if we just subtract out the 15% who haven't seen any of those movies, that leaves us with 0.85. Okay, so we've got our histogram that they've already drawn for us to the right. What can I say about it? Well, it's skewed to the right because if you look at this graph, here's your little tail, right? The tail is on the right side. And we have a single peak right here at 1. So the most common answer was that students have only seen probably the first Home Alone movie, right? And so when I'm thinking about what would be the center of this distribution, I'm thinking it's going to be somewhere between 1 and 2 because those were my most common answers, right? Well, how can I tie an exact number to the center of this distribution? I can find the mean, and I can do that by hand or in my calculator. If I do it by hand, I would take 0 times the probability that someone watched none of the movies, which was 0.15, plus 1 times the probability that a student had watched only 1 movie, which is 0.42, and so on all the way down the table, and it gives me an average of 1.43, right? So how do I interpret that? If I chose many, many students, I would expect on average that they have watched 1.43 movies. Nobody has probably watched exactly 1.43, right? Because that means you watched one and then you stopped halfway through another one. But on average, right, if I take everybody's answer in the long run, that is what I get. We also can calculate the standard deviation. That's done in our calculator, and we get 0.97. What does that mean? That means most people are within 0.97 of the average of 1.43. So if you think about what that means on the graph, so 1.43 is roughly right in here, and 0.97 is about 1. So most people are within about 1 movie of the average, right? So they may not have fallen exactly at the average, but they were close. And that should line up with where the bulk of people are centered on your graph. Okay, so let's talk about another probability model that you can have. And it's called a binomial probability distribution. So think about what binomial would mean. That's a word you may have heard in high school in high school algebra. So the prefix bi always means 2. Okay, so when we refer to binomial situations with probability, we're talking about situations where there are only 2 outcomes. So for example, I flip a coin. My options are heads or tails. Maybe I'm looking at the probability that a team wins a soccer game. Either they win or they lose. That's binomial. Okay? So let's look at this particular situation. The U.S. women's soccer team is doing some calculations to help prepare for the upcoming World Cup, and they are convinced that the toughest matches are likely to end in a tie. These matches require a shootout to break the tie, where each team gets 5 penalty kicks, and they believe they will need to make 4 or more penalty kicks to win. So there are 4 things that have to be true in order for me to do calculations in a binomial situation. So first of all, each trial, which in this case a trial is going to be a penalty kick, right, has to be binomial in nature. So it has to end in success or failure, and those are my only 2 options. So in this situation, either they make the kick or they miss it. If there's more than 2 outcomes, that's not binomial. The other thing is the number of trials has to be fixed. And what I mean by that in this situation is I have to know how many penalty kicks they're going to be taking. That has to be set in stone. If you tell me they're just going to keep going until they miss one, there's no way for me to make any calculations with that because I don't know how many kicks they're going to be making. Okay? The other thing I have to know is how likely they are to succeed. Right? And I mean, that makes sense. If I don't know anything about this team and how many penalty kicks they normally make, I don't know what the odds are that they're going to make any penalty kicks in the future. So in this case, we are told that their probability of success is 70%. And probably that came from just looking at how many they made the rest of the season. The last thing I have to know is that each trial has to be independent. So in other words, when I make penalty kicks, the fact that I made the first one does not necessarily impact how likely I am to make the second one, right? Just because I'm good at it and I make the first one does not mean I'm going to make the second one. So we have an acronym to help us remember those 4 things, and it spells out the word BINS. So I've got that highlighted here on the left. So it has to be binary, independent trials, number of trials is fixed, same probability of success. And in this case, like we said, that was 70%. Okay, so what are some calculations that we can do here? So question number 1 says, what's the probability that the team will make all 5 penalty kicks? So I'm going to reword this question a little bit and say it this way. What's the probability that they make the first one and the second one and the third one and the fourth one and the fifth one? Well, if you remember, one of our probability rules from our last unit was if you are dealing with probabilities and you use the word and, that means multiply. So the way I could calculate this probability is I could take 0.7 times itself 5 times, or that's 0.7 to the 5th. And that would give me the probability that they make all 5 kicks, and that's 0.168. So not great odds, right? Problem number 2 is a little bit different. So it says, what's the probability that the team will make exactly 4 of the penalty kicks? And here's what I want you to think about. This introduces a little bit different variable because there are different ways that could happen. They could make the first 4 and miss the last one. They could miss the first one and make the last 4. They could randomly miss the one in the middle and make the 2 on either side, right? And we have to consider all those possibilities. So we're going to look at those one at a time. So one way this could happen is that they make the first 4 kicks and they miss the last one. So what we would multiply together here is 0.7 times 0.7 times 0.7 times 0.7. That's they make the first, second, third, and fourth kick. But then on the last kick, we multiply 0.3, because if the probability that they make it is 0.7, the probability that they miss it must be 0.3. And when we multiply all those together, that's 0.072. So they have a 7.2% chance of making the first 4 kicks and then missing the third. Okay? But we could also rearrange this, right? What if they made the first 3 kicks and then they missed one, and then they make the last one? Well, again, that still works out to be the same probability of 0.072, because I'm still multiplying the same numbers together, right? They're just in a different order. So here's what I've got to realize. There are 5 different orders that they could miss one kick, and those are listed out here. They can make the first 4 and miss the last one. They can miss the 4th kick, the 3rd kick, the 2nd kick, or the 1st kick. So how do I get my final probability? Well, each one of these arrangements has a probability of 0.072, and there are 5 different arrangements. So 5 times 0.072 gives me a total probability of 0.36. So they have a 36% chance of making exactly 4 of those 5 kicks. So what's a formula that we can use to give us this probability quickly? Okay, so what's happening here is we're taking the probability that they make the kick raised to the number of makes that they have. Okay, then we're taking the probability that they miss the kick raised to the number of misses that they have. And the reason we're multiplying it by 5 is because that's the number of different arrangements of penalty kicks they could have where they miss one kick. Okay? So our probability for binomial distributions has a formula that looks like this right here. And we'll practice with that here in just a minute. Okay? So let's look at the scenario that they give us. And I am going to skip down to example 2 here. It says, you are playing a game called Tsunami Duck Pond, where there are 100 ducks that get pummeled by tidal waves. Among the 100 ducks, there are 20 with stars on the bottom, 30 with circles, and 50 with squares. You must reach your hand into the tsunami and randomly select a duck. If there is a star on the bottom of the duck, you win. After you select each duck, you must place the duck back in the tumultuous water. Okay? And we are going to call W the number of times you win if you play this game 10 times. So why would W be a binomial random variable? Well, there's 4 things we have to check. So first of all, is this situation binary? I realize there are multiple shapes on the bottom of these ducks. There are more than 2, right? But the reason that this is binary is because we're playing a game. Either I win or I lose. And so each trial is either a success, which means I grab a star, or it's a failure, which means I don't grab a star. Okay? Is it independent? Yes, because I am having to put the duck back in the pond after I pull it, my odds stay the same every time I pull a new duck out of the pond. Okay? Is the number of trials fixed? Yes. We are told that we are reaching into this duck pond 10 times. And lastly, is the probability of success the same for each trial? Yes, because there are always 20 ducks with stars in the pond, so our odds of winning are always 20% every time we reach in. So how would I find the probability that I win exactly 3 times? Okay, well, let's break this formula down. The first thing at the beginning is 10C3. What that's going to do in my calculator, it's going to count up all the different arrangements of ways that I could reach in 10 times and win 3. So it'll count up, I could have won the first 3 and lost the next 7. I could have lost the first 7 and won the last 3. And all those different possibilities, all the different ways that I could win 3 times. Then we're going to multiply that by 0.2 to the 3rd power. Why is that? because 0.2 is the probability that I win, and I want that to happen 3 times. Then we're going to multiply that by 0.8 to the 7th power. Why? Well, if the probability that I win is 0.20, the probability that I lose is 0.80, and I'm expecting to lose 7 times. When I type that whole thing in my calculator, I get 0.2013. Okay? What does that mean? The probability that I reach into this duck pond 10 times and I win exactly 3 of those times is just over 20%. It's 20.13%. Now, we can also do this with our calculator. So I'm going to skip down to example 2 on the second page. So we've got a high school here, and they have 5 remaining football games. Construct a probability distribution for the random variable below. So far, LCHS has won 75% of their games. Assume that this likelihood will not change. So this is binomial. Okay, I'm not going to go through the 4 different reasons why. You can do that on your own. But we're just going to go through this table. So what's the probability that they don't win at all? Okay, this one I'm just going to write out for you, and then we'll do some of the others in our calculator. So if they don't win at all, well, their probability of winning was 0.75. So if they don't win at all, that means they lose all 5 games. That's 0.25 to the 5th power, right? And when you type that in your calculator, that's 0.00098. You can also do the last one. So what's the probability that they win all 5 games? Well, their probability of winning is 0.75. 0.75 to the 5th power is 0.2373. So they have almost a 24% chance of winning all 5 games. Now, let's talk about how our calculator can make the ones in the middle a little bit easier. What's the probability that I win exactly 1 game? Well, that could happen in a lot of different ways, right? They could win the first game, the second game, the third game, the fourth game, or the 5th game. That's when I pull out my calculator, and I'm going to go to the distribution menu. And just to show you where that is written in blue right here. So I'm going to click the blue button and then this VARS button. And if I scroll down, you will notice there are 2 options here that say Binom PDF and Binom CDF. So we are going to start with Binom PDF. Binom PDF is for when you are winning an exact number of games. So in this scenario, I want to know the probability that I am winning exactly 1 game. So when I click on this, it's going to say, how many trials do you have? Well, we are playing 5 games. What's the probability of winning? 0.75. And then the X value here is 1 because that's how many games I'm wanting to win, right? So when I put that out in, it does all the calculations for me, and it spits out that my probability is 0.0146. Well, what if I want to know the probability of winning 2 games? I do the exact same steps. I go back to that Binom PDF, and the only thing I'm changing is the X value of 2. And it spits that out for me. So that does make this a little bit quicker, so that you don't have to type out the whole formula every single time. Okay, so let's look at an example where, well, if this will load. Okay, let's look at an example where they ask you something different about a binomial probability model. So suppose you are playing a game with a deck of cards that includes 4 aces, 3 kings, 2 queens, and 1 jack, and the only way to win money is by drawing a queen. That right there is what makes this binomial, right? Yes, there are more than 2 different types of cards in this deck, but I either pull a queen or I don't, and that's how I win the game. So what's your probability of success here? Well, there are 10 total cards in the deck. Only 2 of them are queens, so my probability of winning this game is only 0.2, and that's going to remain constant throughout this game. Okay? So part B says something a little bit different. It says, assuming that this fits all the criteria for a binomial distribution, which it does, what would be the expected value or the mean. So here's what this is a poor way to word the sentence. Here's what we mean by the mean. If I played this game many, many times, how many times would I expect to win? Okay. Well, we are told that we are playing this game with 12 friends. So how many of them on average would we expect to win? The way we figure that out is by taking 12 times 0.2. So we would expect on average for 2.4 friends to win this game. Now, obviously we understand if 12 people are playing, 2.4 of them can't win, right? What that means is if 12 friends played on Monday and then those 12 friends played again on Tuesday and then again on Wednesday and so on average, sometimes 3 people might win, sometimes 2 people might win, sometimes 4 or 1 might win, but that would average out to 2.4. Okay? We also can calculate the standard deviation of this binomial distribution by using the formula the square root of n times p times 1 minus p. So n is just the number of people who are playing our game. It's our sample size. So in this case, it's 12. P is our probability of success, which is 0.2. 1 minus p is our probability of failure. Well, if I have a 20% chance of winning the game, I have an 80% chance of losing the game. And when I type this in my calculator, I get a standard deviation of 1.92. Okay? So what does that mean? Well, if my average is 2.4, that means most of the time when I play this game, if 12 people are playing it, roughly between 4.4 and 0.4 people are going to win, and that makes sense, right? We're not really expecting more than 4 people to win the game, and we're not really expecting, less than 1, right? Okay. So let's say this. Even though there are only 2 queens in the deck, 5 of your friends win money when they play the game. Is this unusual? Why or why not? So let's find the probability that 5 people win. And we can do this in our calculator by using the binom PDF button. So we typed in binom PDF with 12 people playing, a 20% chance of winning. And what's the probability that 5 people win? 0.50315. So while this is not the most common thing to happen, there is over a 5% chance that could happen, right? So while this is not the most common event, it's also not highly unusual. Generally, we look at something as unusual if it happens less than 5% of the time, or if it has less than a 5% chance of happening. Okay? So our last example here is example number 4. Okay, and what they've done here is they haven't actually given us a scenario. They've given us the values of n and p. What do those mean? N is our sample size. P is our probability of success. So if I wanted to calculate the expected value, which is also called the mean, I would take 42 times 0.35 and I get 14.7. We don't know exactly what that means because we're not given a context, but let's just say that 42 people were playing a game. I would expect on average 14.7 of them to win the game, right? We can also calculate our standard deviation using the formula the square root of n times p times 1 minus p, and there it is. Here is the part that I do want to show you. So the probability that x equals 12, you've seen this before. It's just binom PDF. However, D and E are worded a little bit differently. So D says, what's the probability that x is less than 5? Okay? So this is not an exact number. When we talk about x being less than 5, what we're saying is that x could be 1, 2, 3, or 4. Right? So this time, there are multiple things that x could be. That is when we use our binom CDF button. And so the steps are exactly the same as what I showed you for binom PDF. You're just clicking binom CDF instead. So you would type in 42 for n, 0.35 for your probability of success, and then notice I'm not typing the number 5 here because it doesn't say equal to 5. It says the probability that it's less than 5. Well, the next smallest number that's less than 5 is 4. And so the way I interpret this probability this is the probability that x is 1, 2, 3, or 4. Okay? And lastly, E, what's the probability that x is greater than or equal to 19? So here's the thing, the binom CDF button defaults to less than. Okay? So when I type in binom CDF and I put in the numbers 42, 0.35, and 18, that's giving me the probability that x is less than 19. And so then I'm going to subtract that from 100% to get the probability that it's greater than or equal to 19. Okay? So let me know if you have any questions about that. That can be kind of confusing at first. So what I did want to show you, I do have some extra examples down here if you do want to look at those. I also have some calculator instructions and some examples worked out in the calculator down here. I am not going to go over those right now, but you are welcome to look at those. Please let me know if you have any questions.